Uh, Hello everyone. Good evening and a very warm welcome to everyone to today's lecture on economics and machine learning by Dr. Debdatta Saha. Uh, Dr. Debdatta Saha is an associate professor at South Asian University, New Delhi. She has earlier taught graduate level courses in industrial organization and the theory of finance at Terry University, New Delhi. She has also taught introductory finance to graduate classes at the Center for International Trade and Development, Jawaharlal Nehru University. She has completed her doctoral work on network industries, market committees, information revelation, and standardization from the Ast- Indian Statistical Institute, New Delhi. Prior to that, she completed her MSc in economics at the London School of Economics. Additionally, she has worked in some areas of government policy, such as fiscal policy, as an economist at the National Institute of Public Finance and Policy, and competition policy and regulation as an expert in the economics division at the Competition Commission of India. Her research interests are in applied microeconomics, industrial organization, entrepreneurship, and the economics of competition law. Along with several academic journal publications, she has written the book Economics of the Food Processing Industry Lessons from Bihar, India, which was published in 2022 by Springer. She has also written a book chapter on farm facility reinterpretation in the context of COVID-19 pandemic in India in the edited volume of the COVID-19 Pandemic and the World Economic and Social Policy Perspective. It's our pleasure to host Dr. Debdatta Shah on today's lecture on machine learning. Now, I would like to invite ma'am to take the floor and continue her lecture. Thank you.
Uh, uh, Good evening, everyone. Am I audible to everyone?
Yes, Debdatta.
Okay. So thank you very much, Shurajit, for asking me to deliver this talk. And I hope that, it will be something which will be worth your while to spend time on a Saturday evening. So I'm certain you've had a busy day. So I will try to keep things general, as well as, if you want to know a few additional details. But largely, I'll keep this as an introductory talk to give you an idea of machine learning and economics. But let me start with this, that why should we even have a conversation, let's say, like this? Why talk about machine learning, which I'm calling ML here for short, ML, machine learning. And as economists, we are thinking about machine learning. What is in it? So I was thinking of three possibilities of why, as economists, we might be interested, or we might want to know about and want to learn machine learning, or just even to even talk that what we know what machine learning is, something like that. Well, there are three possibilities. One is that we need to keep up with the times, and the fact is that machine learning, if you've seen the Nobel Prizes in disciplines like physics, it's it's a it's like a tool which is entering each and every discipline. I've got good friends in geophysics, and they tell me that every research paper that they're publishing, that something they have to put in, the editors expect them to try out some tools which come from machine learning. So it is not just economics, it is all over the social sciences as well as the other sciences, where machine learning is being used as a tool. And so to some extent that, we might feel that, we need to have an interaction with machine learning just to keep up with the times. Another possibility as researchers is that, we want to go beyond the limitations of existing methods. Now, this is slightly complicated, because this brings up the question that, we are, what are the limitations of existing methods in terms of what, like which space are we talking about? So I'm going to open up that discussion before we even start with machine learning. But then, whenever we say that, we are going to go beyond the limitations of existing methods in economics, uh, there's always a trade-off. Nothing is a kind of solution like for everything. Though if one approaches machine learning as this will give us the solutions for all the problems that we have in economics, and here it would be largely empirical. Whenever we do empirical work, we can bypass all the problems that are there in existing methods. Well, it is not true. So at the same time, when we say that there are to go beyond the limitations of existing methods, there are limitations. We want to go beyond it. We also need to bring up the dangers of the unknown. That is, what are the dangers of these new methods, these new techniques, which are machine learning being one of them. So the first part, limitations, and this, all the parts which I put in with a star, red as asterisk, is to basically be curious about and open to learning this new tool. And the second one is more to do with, slight bit of skepticism as well as kind of critical eye. One possibility is also to say that, this too shall pass. It's just a new phase. It's something which has come in. We should stay with our tried and tested methods of doing, or doing empirical work. And so there's no need, but even if we want to say so, we still need to see that, why are we saying that, are these dangers so big? Are they something that they will really, mess up our discipline or the way we see things? So in each of these three cases, whether you want to keep up with the times, whether you want to go beyond the limitations of existing methods of doing empirical work in economics, or you want to fight back and say that, I will stay with my old methods, you really cannot ignore learning anymore. You have to learn some bit of the jargon, of the way this toolbox is seeing data, and how, as economists, we are, what is the best in it that we can do with what is coming to us. So given this, let me just, first, again, let me first try to, whenever you try to do this, we should I think. So I something else with you, which are my slides. So can you see all of this, these slides, everyone?
Yes.
Okay, okay. So what is, so when we say, whichever way we are approaching the problem of machine learning, let us ask ourselves, what is it? Now, Mitchell, 1997, comes from a very nice book, who has defined or has given the most classic definition of what is machine learning. Machine learning, machines, basically, these, whatever it is learning, these are computer programs which learn from experience, and this experience is E with respect to some class of tasks and performance measure P. And we see that the machine is learning if its performance at performing that task T improves with experience, and this improvement can be measured. It is measured by this performance measure P. So hence there are these elements when a machine is learning. It is learning from experience at a particular given class of tasks T. So what we should be very careful about is what task we are asking the machine to solve, and how we are measuring the performance of whether it is learning or not. So, uh, so the experience of what the machine is learning has to be measured. The learning has to be measured by some performance measure. But then I really like this very commonplace definition, which comes from, data analytics and those millions of other websites which are training people to learn machine learning very quickly. And there it claims that machine learning is basically advanced statistics that computers can perform a bajillion times faster than human beings. Well, yes, it's true. They can perform this much faster, and it's just basically, in some sense, advanced statistics. So, but this hides this definition. Well, that's the neat sum of things. And this definition, uh, none of these I feel do really justice until you dig yourself. You start with the red flags first. Is the machine really learning, or is it just machine memory? Now, this is something that I, as a social scientist, I'm a bit skeptical. When you say you're learning from experience, the dimension of your learning is basically coming from or how whatever you're measuring, that is coming from the measurements and everything. The branch of mathematics which is supporting machine learning is statistical learning theory. So I'll come to this next slide. So maybe we are just looking at, because this bajillion times faster, and this is because computers have a lot of machine memory, and so they can so we are basically talking machine memory and not really learning in the sense that we understand learning. Then, of course, next red flag, what is the relationship between artificial intelligence and machine learning? And the next one is that if you talk to any mathematician and you talk to computer scientists who are experts in machine learning, you will see this uncomfortable relationship there, because the mathematics of machine learning and the applications of learning, there is a bit of a divide, because it's a part of machine learning which is well founded in statistical learning theory. But the more advanced models, neural networks, deep learning, the mathematics of that is not really still well developed. So essentially, what gives rise to how is the machine really learning, that is not that well understood. It definitely does learn something, but the mathematical foundations of that is not. With the first red flag, and for understanding learning, let's look at a few insights from psychology first. What is learning and its objective of learning? So we keep the machine part here aside, and first let us focus on the learning part. So learning, at least human learning, is basically trying to figure out new patterns. So you have to put some old patterns of doing things on rote mode, free up some mental space so that you can actually learn new ways of doing things. Now, Kahneman and Tversky have actually talked about how heuristics are, the usage of heuristics, because this is how we start. Actually, an efficient usage of our brain power is that we create some things which we call fixed patterns or heuristics, store it in our brain, and these become our habits or our habitual tendencies. And then the freed up mental space that we have, with that, we can learn. We can learn new patterns, and we can absorb new information. So finding patterns with data, and all of this is finding a lot of application in studies and with situations like Alzheimer's, where apparently the brain really cannot learn anymore or find those, or even lose those old heuristics which were stored in the brain. Now, interestingly, the human brain is surprisingly efficient at, this is very important, efficient and working efficiently. So I'm using this separately again in for within stimulus poor environments. So what is a stimulus poor environment? It is a small thing like you tell a child that this is a car, and the child sees the car, and the next time the child sees a similar object moving down the road, recognizes it, puts it in its the image that it is stored as a car, and labels that as a car and says car. Okay, so if you've shown the example of a car, then the child is able to recognize a car. So this capturing and retrieving of information data recall as evidence of learning. Now, how will you see this with machines or basically computer programs? How do you see this kind of non-sentient entity, which is a computer program, learning? Now, uh, now this learning, when you talk of learning here, purely the machine as the machine will learn. So some patterns you will show the machine, and then the machine will recall and come back to you with and say, and you put a correct label to it and say, okay, this is the pattern I saw earlier and I'm seeing this again, so I've learned it. Now this does not mean it can mimic human thinking and rationalization. That part of behaving like a human being, given that I've learned what I had to learn, and on the basis of what I learned, now I start acting upon it and so the mimicking of human thinking and rationalization of what I learned, that comes under artificial intelligence. So when you go towards intelligence, you are asking for a lot more than pure learning. So the learning part can purely be that, I show you a certain set of patterns, and then I ask you to recall those patterns, and you effectively can do that. Then, well, maybe we say we have learned. But on the basis of those actions, can you really say what you're going to do with that learning? That is the subject matter of AI, and that's artificial intelligence. So that's one red flag I hope I want to put past, uh, so that, for machine learning, reasoning is not important. Uh, when you are learning for human behavior, from learning to acting upon that learning, there are effectively three stages. When we are learning new patterns, we retrieve from memory whatever we have learned. Then if we find that something that we are labeling incorrectly, we are incorrect about it, we correct it, that self-correction, that is also a part of learning. So so you show a child, let's say again, a car, and a new kind of car comes, and the child is not able to, label it correctly, thinks instead it's a cow or an animal. But then if it is told that, no, this is still a car, well, then that, and it is corrected, then, well, that still comes under, learning. In fact, that is called reinforcement learning. But then then to go beyond it, to mimic human behavior, you would need reasoning, and that is the arena of artificial intelligence. And to that extent, machine learning is not very new. It has been around for quite some time, and it has been used in various contexts. So let's start with an idea of learning a target concept. Now, this was as a very old parlor game, 19th century parlor game, which was called the game of 20 questions. Okay. So I'm certain all of you, it's online, so I'm not meeting you face to face. But if we had, all of you might have participated earlier in this kind of a parlor game that we ask you to think of maybe a celebrity or movie star or something, and then we give you the options that, you can be like a detective, you can ask questions, but the questions can only be yes. So the answers to your questions will be only in the form of a yes or a no. So you can ask, is the gender of the person, right? And then you can ask, maybe roughly the location, the country, which movies, Hollywood, Bollywood. So you keep eliminating at every stage to narrow down your learning from those yes, no answers of the people who you're asking those questions. From those yeses or nos, you're narrowing down slowly to the actual correct identity of the person, which has been thought of at the beginning, and you're asked to guess. So the strategy, because here you see if you have yes or a no, so there are two possibilities. You're asking 20 questions. So 2 raised to the power 20, you have these many objects already that you have to distinguish between, you have to classify between as correct and incorrect, a kind of binary classification that yes, this is probably in the correct guess, and that is a wrong guess. And an efficient strategy in this kind of learning is to ask a question that will split the field of remaining possibilities roughly in half each time, because then it neatly gets into a yes or a no. That's the strategy. So, so you have to ask cleverly, you have to ask to that, so that this kind of parsimony, because you're limited to only 20 questions, so that is a very important aspect which will come up in machine learning when we talk of training data and the limitations that we already have when we try to learn with a fixed amount of data. So this kind of learning a target concept has been around informally from these parlor games long back. And now when we want to conceptualize this and formulate this kind of learning, uh, humans are learning these concepts too, like, for children, as I said, it may be a car or a dog. As slightly older adults, we are asking questions like, should I study more to pass an exam, or what is the optimum number of study hours? We learn it over time with experience. So concept learning. So the idea here is each concept should be viewed as describing some subject or a subset of objects or events defined over a larger set. So whenever you're trying to understand this concept, you want to understand dogs as a subset of animals, of which dog is a subset. Or each concept now mathematically can be modeled as a 0 1, a Boolean valued function over the larger set. So you can think of, if it is a dog, then the value is true. If it is any other animal, then the value is false. So kind of true false, which this idea is built into these parlor games, these 19th century parlor games, when you're trying to learn this. And the task, because this is how we began defining machine learning as per this definition, your computer has to be given a fixed task that, that is, if I give you an image, or I give you an image of a dog, please identify this or classify this as a dog. Well, then that's the task. You have to learn to classify it correctly. So this is called, typically this task would be a classification task. So automatically infer the general definition of the concept, given examples labeled as members or non-members of the concept. So here, this kind of concept learning has this idea that you are going to be given a set of labeled objects, which are a part of a larger set of objects. So I'll create labels over the entire animal kingdom and have a subset of them labeled as dogs. And it may be many kinds of views, frontal view, back view, all kinds of views of a dog, and then feed it to a program, a computer program. And even if it is fed the picture of an animal, any other kind of animal, it will be able to identify a dog if it is. So the task is, this kind of a task is classification. These are called classification tasks. And this has been very common. This is a very common application of machine learning. So here the problem is of inferring Boolean valued function, to be very particular, from training examples of its inputs and output. So the idea is, whenever it's a dog, it is true. So I want to understand this. I want to infer this function. So all of my learning becomes inferring a Boolean valued function. So this is what we are trying to work with. So before I proceed, maybe I should stop here and ask you, do you, because it is kind of online thing, and I don't know whether there are any questions already, but is there any clarificatory question or anything that you need me to, explain a bit further, or somebody has a comment before I go ahead? Or should I just continue?
Is there any question?
When you say Boolean valued function, are you meaning to say that it is like a yes or no sort of a thing?
Yes, yes.
Hmm.
What I mean is the Boolean valued means it will take a value like
Okay,
0,
binaries.
1 or yes or no. So
Okay.
that is the idea of a Boolean valued function out there for that concept learning. So this part will make this clearer. Okay. So is that from Krishna Kumar?
Yes, yeah.
Yeah. Okay. So I'll make this clearer to you. So when we are now, can you see this uh, PDF slide?
Yes.
It's in
Yes.
my
Yeah.
hand.
Yes.
Okay. So what I'm trying to do here is trying to show you machine learning, what it is really doing when we are talking of this application of concept learning. In reality, if I'm thinking in terms of its mathematical structure, because I just use the term Boolean valued function, machine learning as a mathematical problem falls under a class of problems which are called ill-posed problems, badly posed problems. So a typical mathematical problem has, you have input, which is you have input given to you. Then the output Y comes to you through a particular operation, a function. So the input, this function is typically known. And this function, consider this function as simple addition, the operation of addition. So the input can be two numbers, let's say 2 and 2. And the addition that you do is 2 plus 2 gives you 4. So the output Y here is 4. It is coming to the function here is well known. So you're going through a function, this various kinds of functions, this F is known. On the other hand, so this is called a well-posed problem. This is a traditional mathematical problem. So all our problems of integration, differentiation, addition, whatever we think of, the standard mathematical operations come from these well-posed mathematical problems. On the other hand, machine learning comes from a class of problems which are called inverse problems. And the interesting thing is inverse problems never have a unique solution. Now, what do we mean by inversion? Inversion is happening like this. So this will again take me back to a little bit of idea. I'm introducing a terminology here called training data. So what do we observe in reality whenever we work with empirical uh, so let's go back to our example that we are working with the situation that we want our computer to our program to identify dogs as a separate category which stands out apart from the rest of the animal kingdom. So I want the computer to identify anytime it sees the image of a dog, correctly classified as a dog and not as cats should not be labeled as dogs, lions should not be labeled as dogs, as well as dogs should not be labeled as lions, dogs should not be labeled as cats. So a kind of correct classification. So this I going from 1 to L is basically the training data, which can be thought of now as images, various kinds of images, frontal, backside, every kind of images of all animals, including images of dogs. And the output here is the output, the Boolean valued function that we were talking of, is that if it is going to do a classification, if it is a dog, it will give you a +1, that is the output, and it will give you a -1. So two possibilities. The output is basically binary. The yi here is binary. So the yi will take a value +1 if it is a dog, and the yi will take a value -1 if it is not a dog. Now, Dr. Krishna Kumar, is this clearer to you what I meant then?
Yeah, yes, yeah.
Yeah, the Boolean valued function. So that is what I meant when I talked of this Boolean value. Just that. See, the problem here, the functional form which you will get, which will translate this input to this output, is not known. It's left free. So this is the inverse problem. What function translates your input to output within this training data is not given, is unknown, is an unknown function. So the whole purpose is to guess that correct functional form that gives you that classification. And that is the problem of machine learning. So it is called this is an inverse problem. And so inversion creates a lot of problems. You cannot really solve a problem till it becomes a well-posed problem. So machine learning tries to, from this position, from what converts this this input to this output, from this to a well-posed problem, it tries to do so. Note one thing, by the very characterization out here, ML problems are black boxes because this is a classic black box. The machine will see, you really cannot know how you can guess at some of the stuff, but this is a black box in the sense that how it will see the pattern, you will not be able to give an answer to. So to keep you alive to this, what are the dangers? There are some dangers of the unknown. There are certain benefits of going away from the standard traditional mathematical problems to this kind of a new approach, not so new, but new for us as economists. So, but there will be certain trade-offs. There are certain problems which will come with this. So we will have to convert this ill-posed problem to a well-posed problem, which is very mathematically challenging, so that learning can be achieved. So what we are going to do right now is we are going to feed this computer, this thing, labeled data. So labeled data will be basically these xi, so maybe L data points, and think of this as at least 1000. Okay, so here we are introducing the idea of big data. Suppose you have access to a lot of data. So 1000 images of animals, okay, which are now labeled as in this way. Yi will be a +1. This is also labeled. Both your output and input is labeled. If it is an image of a dog, output +1 is +1, which means it is a dog. Then the next image, x2, can be the face picture of a lion, and this will be a -1, means it is not a dog. So 1000 images, which includes images of dogs, and 1000 such +1, -1, +1, -1, whichever, when it takes the value +1, whenever it is a dog, and it's taking a value -1 whenever it is not a dog. Because everything here is labeled, this is called supervised learning. Because in this learning procedure, the the programmer is providing the machine labeled inputs. So whatever the machine has to learn, everything is labeled. As opposed to that, there is something called unsupervised learning, and that is used in the context of text and has a lot of applications, but I will not go into that. It's best to start with something, at least talk about something in a bit more detail rather than introduce straight off everything. But this is basically the idea of supervised learning, which we are trying to do. And the whole idea will be that the total sample available to us, so a sample size of 1000 images, which will now be split partly into this part is what we call training data. This I going from 1 to L points, these 1000 points, the total 1000 points that we have is we can split. So here actually I'm assuming this in a slightly different way. So the idea is you have the total sample available to you is more than the size of the training data. So the training data here is going, if it is 1000 data points, you have more data available to you, more than 1000. So suppose you have 1500 data points. 1000 data points is used as training data, which are labeled. So labeled as +1 and -1 in this way. And the test data is unseen data that you hide from the computer and where you test out the learning of the computer program. It's like taking a little class test and to see whether, so if you have 1500 data points, which is the total size of your sample, you do not give the entire sample size up for overall analysis. You withhold part of it and you call it unseen data, test data. And this 1000 observation sample point now given to the computer and you ask it to learn from that. So out of those 1000 points given to you, you try to learn that, this is the concept of a dog. This was a classification task. Through this, the computer will be able to classify images because they're all labeled dog and not dog. And then in the test data, 500 images of all kinds of animals. Now you test and see whether the computer is correctly labeling, classifying dogs and other animals as not dogs. So that is the idea of concept learning. So any questions? Is this clear what we try to do here? Yes? Anything?
Is there any question? Any clarificatory question?
So, let's take this to a more applied example that we often do in economics. Let's apply the idea of concept learning to something as economists we are, at least I do this kind of work all the time. So this would be, the work that I do involves prediction. So, but here I'm not seeing this as a prediction problem. I wanted to classify. I want to see this as a classification problem. Suppose I want to see this as a classification task. So I measure firm performance using a standard measure of financial assets. Many other things can be used. You can use Tobin skew. You can use other financial measures, which is, standardly done. And then there are these instances, which we call, these are what we call, these as variables which are, which we call here attributes. In our language, it would be independent variables. And we have some proxy for firm size, proxy for firm age, proxy for ownership type, proxy for the investment strategy of the firm, proxy for quality of assets, and proxy, some measure of competition that firms face in the market. Now, I want to, without going into all the mathematical details of this, I want to understand the concept. So to understand the concept of, I wanted to label firms as a good performance firm, high performance firm, and a low performance firm. So I have a set of hypotheses. Okay, so a hypothesis is so these are the attributes. The attributes are your independent variables. So you have size, you have age, you have ownership, you have investment quality, you have asset quality, and competition. Instances are the various, the sample size that we're looking at. And in each of these, we have these different attributes. Now, a hypothesis is like a constraint on these attributes. And the constraints are, let's put only binary constraints. So the size, something like this. So a hypothesis is a conjunction of constraints on these attributes. We are assuming each of the attributes can take two values, like size can be large or small, age can be old or new. Just for simplifying everything, ownership is private or public. Investment quality can be good or poor. Asset quality, high, low. Competition, low, high. And performance is high or low. So a particular hypothesis structure is something like this. Just give me a second. I just lost my PDF. So just give me a second. I'll just show you the... So a hypothesis here would be something like this, that I want this firm to, this computer to understand if I feed it some of these instances, that, high performance, one possible hypothesis can be about firm performance, is this. This is the most general hypothesis. Every instance is a positive example. That means I put no constraint. No constraint. This is everything can take any value. Right now, there is no theory about firm performance. So nothing dictates, or there are no constraints on firm size or firm age or ownership or investment quality or asset quality or competition. So this is the most general hypothesis that I can think of about firm performance, that there is no, or basically it can take any value. It can be high or low. And this means everything, every instance, be it high or be it low, will admit itself to a kind of permissive performance, number. As opposed to that, a most specific hypothesis will be no instance will give me, nothing. So basically, it means that none of these attributes really matter for explaining firm performance. So these are two extreme hypotheses that I have, that we can have. But the task for the machine is to learn the concept of the set of instances where performance is high, where I feed it a certain class of hypothesis like this. So this is your labeled training data that I have created across 4 instances. And here I have found that if it is large and old and private and good and high and low, performance of the, as measured by ROA, is high. And similarly, like this, I have 4 instances. I feed it to the program. And now for unforeseen X, so these will be your independent X variables, I would want the computer to now correctly label it as either a high performance and low performance. So to do this, one simple, very simple algorithm is called, and it's a very, very bad algorithm, is called find S algorithm. And you start with a very, very specific hypothesis, which basically means that none of this theory makes any sense, that none of this, set everything to a null value. So we start with phi everywhere. And then we look at the first instance where it is labeling it as a +1, as a high performance, because that is what we want to find out. And we find the next instance where this is also a high performance. But if you say that, you stop your learning here, this is on the basis of a very narrow sample point. So here, when you feed, so the first point that you give it, and it labels it as a high performance firm, you try to move from this learning to the next level of learning, large has become small. So you tell the computer, this now becomes a question mark. So you really cannot put any constraint on this. So you really cannot put a number. So large, so instead of large, you can keep it as a question mark. Old has changed to new. This also becomes a question mark. Private replaced by public. So this becomes a question mark. But this pattern remains same. Good investment quality remains as good investment quality. High asset quality remains as high asset quality. Low competition has become high. So this also is replaced by a question mark. And then in the label data, so it is high, remains labeled as high. Now, the next instance is a low performance, is a negative, is a -1. So now, when you feed this to the computer, these 4 instances, you can find from here, if it is correctly, you have an underlying theory, like you know what is a dog, and you know these labels. You can, if it is a dog, you would put a +1. If you have a good theory about what determines your firm size, and these are the typical variables, and you know for certain that investment quality and asset quality matters, well then, by feeding in negative instances, the learning will not change. And when you do this, so you move this from one instance to the other instance, you will keep replacing. So like large, old, private, good, everything gets replaced. Everything becomes a question mark. Finally, the algorithm will only keep good and high as the patterns it has learned from the data, as when it is likely to see a good or a high ROA. All others, it's a question mark. So you really cannot put a value out there. So next time when you see, you wanted to classify a firm into a good performance or a bad performance by ROA, it will simply look for measures of investment quality and asset quality. And with that minimal information, it will start classifying firms into positive and, whether it's a good firm or a bad firm. So this is a kind of algorithm which is doing this, which is trying to learn a concept, which can be something as simple as image recognition, which is done for multiple classification tasks like spam filtering. So here I will stop the slides and in fact use a whiteboard out here. So this does have a whiteboard. So I'll just use my whiteboard and show you some. This is the whiteboard. I hope you can see this. So we are now talking of classification tasks, which can be done with machine learning. So with machine learning, you are trying to find that functional form. F in a particular way. There is a method to learn this also. So I'm not going into the technicalities of that, but the whole idea is, if you have labeled data, and the data is basically something like dog and not dog. Similarly, you basically have output here. It is +1 and -1. I would really request nobody else annotate on the whiteboard when I'm writing, because I think it's showing up as other things out here. So similarly, if the label data can be something like not just this, it can be, in our other example, it can be you wanted to learn from a good high ROA, return on assets. There are ways in which you can, and these are labeled as +1 and -1. You have certain label data which you will feed to the computer as training data. And in the unseen data, it will do a classification. It will classify firms into high ROA and low ROA. So by its performance, it will show the firm performance. So this is a very important set of applications of machine learning where this kind of learning is being used. So it is also this comes under what is called supervised learning. But as you can see, there are a number of things which I'll talk about the technicality of this right now. So let me show it to you from this. So when you want to find that function f, you fed it some training data. You want it to have a good approximation over that unseen data. So you trained your data and you showed it, in these instances, it is a good performing farm, or in these instances, it is a face of a dog. Now you want this function to work for any arbitrary x, not only for the part that you trained the data for. Now, this essentially, even though the functional form f that you hear is unknown, the basic challenge, the basic assumption of which comes from statistical learning theory in this in machine learning is that the training points in your training set and the future points in that test set in the unseen data, they are independently IID, basically independently and identically distributed according to an unknown but a fixed probability distribution, PXY. So these are called agnostic, distribution agnostic or distribution free statistics, which is the point out here that you want a good approximation for unseen data, and you want to propose an evaluation of this, how well this you want to evaluate this goat basically. Did it perform well on that unseen data? How well did it perform? And that you use using a concept called a loss function. Now, depending on what you use as a loss function, you can have quadratic loss functions and many other forms of loss functions. And I'm not going into the technicalities of that. But depending on what is your loss function, the whole idea in machine learning is to find this f, that you have a good approximation in this kind of unseen data where it is going to do the job. Now, let's see what happens when you have these blue points are your data points. Now, in standard statistical analysis that we do as economists, we are used to working with. So these are our sample points, and we can fit a straight line. This is a very simple functional form. And on the other hand, we can fix because here you can see this is what we are calling the labels, the label data. So let me show you what you have is up to this point. This is X1 to XL. And this is your Y1 to YL. This is what you have available to you as training data. This is available to you as training data. So all of these X's and Y's are available to us as data. Now, a simple idea is to do a linear fit through this kind of data. And we know that we know we measure the goodness of fitting a straight line to this by observing the deviation from the actual data points like this. Now, that is the way to assess the performance. Typically in economics, the way we approach our empirical work is if we have sample of data, we treat everything in the sample and we assess its performance with ex post diagnostics. Like, we have goodness of fit measures, we look at adjusted R squares, we standardly check whether how much of a, whether how good our estimates are, consistency properties and bias, and all of the standard measures that we have with which we can explain this. Now, on the other hand, if I have data this, have a part of this as, so my total sample available to me goes beyond this. So the total number of observations goes beyond XL to some XN. And from, so this is XL and this is YL. And there is some unobserved YN. So this is the total. So available with me is what is called your training set, which has these labeled data, which is this X1, Y1, going up to XL, YL. And this part of my data, I now use and I fit anything to it. The simplest thing to fit, as I said, would be a straight line like this, a straight line fit. I can also fit a very complicated functional form, the one that you see here in red. Because in machine learning, what I fit, this F, this is unknown. This is what we are going to discuss, or we're going to discover. So apart from this training set, there is now a test set. So this is also part of our sample, which is available to us. And this is going from XL plus 1 to YL plus 1 to some XN, YN. Now this part, I'm going to test how well the learning happened. So here, you learn what you learn here is what is this best fit? What is the best fit to the data out here? What explains the relationship between the X points and the Y points? And the problem is, if I fit a very complicated functional form here, essentially the best explanation for everything out here will be, I can fit this squiggly red line. It will explain so it goes through each and every data point out here, and it explains everything, every point out here. But the moment I take it to outside the sample into this unknown test set, in this unknown zone, it is unlikely to perform as well as it is doing within the test set. This is standardly called the problem of overfitting, because you fit a very complicated pattern out here, which is very specific to the training set that you have. So one standard idea here is that of generalizability. You have to generalize beyond the training set. Whatever you've learned, your learning has to generalize beyond the training set into the test set. If you fit a very simple line, straight line like this, well, then you do not, your approximation within the test set itself is not a very good approximation. So this kind of a very simple fit has a high bias within the training set itself. And this kind of a very complicated squiggly line, which is very complex, F complex, has a very high variance in the terminology of machine learning, which, if you are interested, I can send you a lot of references to, which you can follow up and get back to me if you're interested more in it. So this interplay basically means that, again, the trade-off which opens up is a high bias versus a high variance. Should I fit a very complicated squiggly out here, which does a very good job in the training set and performs miserably outside the training set, which is called the standard problem of overfitting using complicated functional forms? as opposed to this one, which is using a very simple functional form, which is the problem of underfitting. So this kind of trade-off basically means there is a sweet spot out here, which is the optimal amount of complexity to use while fitting the functional form. As you can see, that's what we said. And any inverse problem like this, there can be another complicated squiggly there's no end to how creative we can be. And therefore, as we said, there is no unique solution for this kind of machine learning problem, because the way it is to be seen as a ill-posed problem, which admits multiple solutions. So how do we deal with that becomes the big subject matter, which comes with machine learning. What I want to leave you with, because this idea of training set and test set is something that we do not do in econometrics, that we do not do in empirical work. Now, why would we want to, why would we want to even, because when you want to do this, as economists, you will have to split your sample into two parts, a test set and a training set. Now, it is becoming very common when we say keeping up with the times, that we actually have a part of our data where we test out, which we use as test data for our model, where we test the model, and a part of the data which we use up as training data, as training set. Now, this kind of training, as you will clearly see, learning happens better the more the labeled observations that you have, the more you can train your model. So the point is now, as Halvarian mentions in his, he mentioned it long back in a very interesting paper, which is, again, I'll just show you that example. Let me just see if I can share that paper with you. This is the, using an example. In this paper, Halvarian, and this is in 2014, it's a decade back, claims that, economists now have access to a lot of data. So in social sciences, we have a lot of data. Social media gives us access to data. There are also markets where, like airlines, you have dynamic pricing. You can get other markets where the dynamic pricing, you can have minute by minute data or daily trading data, stock price data, where you have a lot of data. Paucity of data is not a problem. So you can actually be generous with how you treat your data, which you have access to. You can split it up into two parts, into training data and test data. Your model, whichever model you want to fit. And what is the advantage of doing machine learning? It lets you fit incredibly flexible functional forms, because the F is unknown. You can fit an incredibly flexible functional form, which will also perform well in test data, as long as you have big enough data to test your data. Now, this is the example that is a very interesting example about the Titanic survivors. This is a example which is used here. This is a classification tree example. This is a machine learning technique, which is now very common. It's a regression tree method. It's called it's a classification tree, which we are talking of here. It can also be used as a regression tree. So this is also a classification task, which can be done in the standard econometric way, which is we are used to this term called logistic regression. Most of us know this. Now, this is a very interesting example which Halvarian gives to motivate the whole problem. And the problem here is trying to predict the survival, who survived the Titanic tragedy, the survivors of the Titanic accident. And if we assume that age of the passengers as an important independent variable, well, the logistic regression, if you run a simple survival versus age logistic regression, he finds that age is an insignificant predictor of survival, the probability of survival. But when he runs a classification tree of this, where there is another layer, which is, this is the class of travel, first class, second class, and third class. But independent of this layering, whether it's a class of travel or age of travel, the regression tree catches a pattern, sees a pattern in the data, which is this. It is that the survival age did not matter. So if you see in the classification bins out here, which was done using the classification plots using, if you just plotted the data, these, the ones which are crosses are all deaths and the circles are survivors. Now, independent of class of travel, they, across all the three classes of travel, passengers traveling, there is a highly nonlinear pattern with age. That is, if the age is below a certain cutoff, and in fact, it is seen that age less than 8.5 years, children had a much higher probability of survival, and people above the age of 60, okay, senior citizens across the travel class had a much higher probability of death, of lack of survival. And in the intermediate range between between 8.5 and 60, age really did not matter. It was like a fight for life for that. So it seems there was some humanity. They were trying to save the children in that Titanic tragedy, and it did not matter whether they were children or not children. So this nonlinear pattern is caught by that nonlinear f function, which if you allow for a more flexible functional form to be fit into the data, which can be done with machine learning. So one possible argument in favor of using a new tool like machine learning to our kind of work in empirical work in economics is to allow for nonlinear patterns in data. And the nonlinearity could have been even more, like, age within certain ranges. And it is very hard to do this kind of nonlinearity. It can, various kinds of squiggles can be fit in. That can be done much more easily with these new techniques than without these techniques. So that is one possibility. But you can always claim that, I can replicate this with nonlinear models. Well, yes, the extent to which, and I'm not arguing in favor either ways, but learning these target concepts into machine learning, particularly I've been just discussing supervised machine learning, where everything is correctly labeled. There are now multiple ways of doing this, but then it has got now a number of applications. The biggest defense for this, as I said, part of it is that we do have a lot of data. So, and you can see the applications are in these kinds of customer market segmentation, where you can have very complex learning patterns, and you have a lot of applications. You can also have reinforcement learning, which is a separate class. So now, if it is learning that we are interested in, then there are separate tasks. One class of tasks are called classification, that we have been discussing, that you label and classify between good performing and bad performing firms, dogs versus non-dogs, low elasticity of demand areas or neighborhoods from high elasticity of demand areas, income groups. You can do classification. These are all coming under classification problems. Machine learning techniques, by finding out these complicated patterns with F, and these are various kinds of these classifiers, naive-based decision trees, random forest, support vector machines, K-neighbor, KNN. These are techniques for doing that. Regression is one other approach which can be done with machine learning. Within supervised machine learning, there can be classification tasks and regression tasks. So you have lasso and ridge regressions, decision trees. So these are various possibilities. Apart from that, when it is unsupervised learning, which is used in text, there is a lot of applications which are when we use text as data. And so I think I've already used up a lot of your time. So if you have an interest, I will walk you up that path. But I want to just add it here, like, should we learn machine learning because it is trending, or is it useful? The extent to which it is really useful. And as someone who's been applying these tools, I find that yes, it is useful, but it is useful in a very fixed set of contexts. And the real power of machine learning really comes out in when we talk of prediction as prediction algorithms. These are also called prediction machines. So machine learning, there are a lot of applications which I mentioned out here, which I don't have time to cover. But I've talked about this in many contexts, that, in business economics, where you have to do a lot of work on prediction. Typically, these are classification tasks, but also prediction tasks. So the major area where machine learning is finding a lot of applications are all in this finance, and where, for two reasons. A, as I said, the standard way is that you need data, you need training data, you need a lot of training data to be able to, and then you have to test your work on this test data. So in these tasks, credit card detection, stock price prediction, so be it is a prediction task or a classification task, machine learning tools seem to have an advantage over our standard toolbox in econometrics. And there are a number of examples where these are very recent papers where forecasting techniques have used, all of them, not only your standard tools from nonlinear or linear time series analysis, also used machine learning tools like neural networks, because they seem to predict better. So it is to some extent in their ability to predict that we are using them. But when we use them, note that in social sciences, we do not have a common understanding yet of machine learning algorithms. Some people think of this, as prediction purposes. Some see that, they can be used also for causality analysis. But it is quite clear that, this is only the Bremen paper which say that, these are two different cultures that you're talking of. One is our, that we were to look at data in econometric for sure. The data generating TGP, model it in a particular way. You go from statistics up that route. And this one is an algorithmic modeling culture with a very different view. And this comes from inductive learning process. So our way, always very deductive. We had a deductive approach to our methods and analysis. This is a very algorithmic culture, is a very inductive approach to data. Is it very useful? To some extent, there is a very clever application, which I don't think, I'll only talk about it if you, this deductive versus inductive, there is a lot of debate. But there are a few people who have said that there is a lot of power for inductive inference. You can actually find new research questions to ask if you use machine learning tools, particularly unsupervised machine learning using text. And with text and using this, there are a number of applications which have been able to generate or see patterns within the data. At the same time, being these algorithms, at the end of the day, the first picture that I showed you, there is a bit of a problem because it is a black box. How the machine really learned, you will not know. So what you read up when you go for machine learning, you might be able to predict well. The prediction performance of a machine learning model might be much better than a standard, even a very cutting edge nonlinear time series model. And yet the reason, the why of it will not be very clear. So it is not. So a lot of cutting edge work is now happening into making this interpretive machine learning, where they are borrowing from tools from economics and game theory to make machine learning more interpretive. But as it stands, and if I may summarize the stuff that I've been talking about, machine learning basically says you can go straight to the data. You don't for problems for which you have a good idea or a hypothesis which are well structured, like the ones that I said, that you more or less know what are the markers for credit card fraud detection or firm performance. You kind of know these are the markers. Well, then you can set up, you can basically say that, in these tried and tested grounds, I have a lot of data now, and now I want to basically uh, fit an algorithm which will be quite complicated, so that in the unseen data, I will be able to predict well. Well, therefore, it is unsurprising, and in these applications, whether it is unemployment rate prediction, exchange rate forecasting, or GDP growth rate forecasting, now casting the GDP growth rates, you find, particularly in macroeconomics, it is machine learning tools which are starting from support vector machines. So there are these various Fs that we are talking of, that you can apply these functions. But if it really matters to you what you want to talk about here, you need to go beyond machine learning to, probably look at some other things. And so I think I shall open this up for questions. Shurajit,
Yes, thanks a lot, Debdatta.
yeah,
Can you stop sharing the screen, please?
yes.
Okay. May I request the participants, if possible, can you switch on your video modes so that Devdatta can see some faces? I mean, it's, if possible, please switch on your cameras. Now, please ask some questions if you have any. In the chat box, I don't see any question per se. Do you have any question, anything?
Hi, good evening. Am I audible?
Yes, yes, Akriti.
Yeah, so Akriti here from Dolasram College. First of all, a big thank you to you for organizing this and for ma'am for delivering it in such a poised manner. So I have some clarifications that I want. First
Mm.
one is that can we consider ML as a subset of AI? Like if we draw a Venn diagram, so can I make the bigger circle as AI and then a smaller circle within AI as ML? Will that be a good idea? Like, or
Uh,
am I wrong in understanding?
why would you want to do that? Is my first question.
Because most of the time, we are throwing around ML and AI, ML and AI, it's,
Yeah.
they're coming together like big data and ML, so I
Yes.
am very difficult. It's getting very difficult for me because I don't have this as my research forte. Okay. So I'm just looking it in the
Yeah.
newspapers, in the columns. So I don't
Yeah.
have any idea like what it
Yeah.
all is about. Okay. So for
Yeah.
me, I need to, I have this habit of, compartmentalizing everything so
Right.
that
Right.
I
Right.
have a clear idea of what I'm talking about when I'm talking to the students, right?
Right. Right. Right.
Yeah. So
So
when you
you're
talk
asking. So
search,
if I may say so, the whole so artificial intelligence is potentially the last mile that you want to walk to, right? So
hmm,
yes, intelligence is with it comes an aspect of reasoning. So when I began talking about this, I said you move from learning to intelligence. So uh, ML, yes, is a subpart in that sense that you have a certain, and this is basically inductive in approach. So you have a large number of instances or empirical observations, and now you move from those instances or observations to some sort of patterns that you've seen in the data, or the machine has seen in the data. Now, what you want to do with that decision-making rule, that is absent in machine learning, but that is present in artificial intelligence. There are a set of rules with which you can now decide how to act upon the learning that you get from the data. For machine learning, for instance, if it is a classification task, you set the task. And after the task, you whatever is learned, you check whether it is well learned and you stop there. Artificial intelligence, the whole purpose of that is to add a layer of reasoning, which that layer of decision making, and that decision making is absent in machine learning.
Okay. Okay, got it. And one more doubt I had, that was related to big data and machine learning. Like, again, they are again used synonymously. Together they are getting used, big data and machine learning.
Absolutely, absolutely. So let me talk a bit about that. You see,
Yeah.
the whole idea here, as you could see, it is inductive. That is, maybe I have some underlying hypothesis. I have some ideas about how a process is working, but I'm also curious about there might be other patterns or hidden patterns in the data. So I want to set up some structure like this, that there are some some factors which are explaining a process. So as the example that I gave of firm performance, for instance. So I the point is how well a machine, so the machine is expected to learn from given examples or instances. When I'm talking of supervised learning, I'm labeling everything, like I'm giving it to the computer. And so the typical split which is done, if the total sample which is available to you is, let's say, some 100 data points, at least 80% of that data points have to be set aside for the machine to learn. So that is called the training data. So typical split sometimes is 80% and 20%, or 70% and 30%, or at least 70% of your data will be set aside now for the computer to learn. If, as you can see, if you have very large data, setting aside 70% of your data or 80% of your data, because it is very data intensive, that this is the problem. The difference between human learning and computer learning is that we work, as we said, in a very stimulus scarce environment. A little child, a small child can be shown one or two instances of a car, and by the third instance will correctly start labeling correctly and correctly label car from a truck to other objects. But for a computer to be able to do that, to do simple, this is not AI, this is ML, to correctly classify this, will require you to give it a lot more, because you are trying to ask it to learn everything. It is not intelligent. So maybe a frontal view, a backside view, a top view, an aerial view, a partial view, the kind of fur it is seeing. So the more images that you can feed in. So the largest applications of these, if you are interested, would have been, you might have heard about it, is in spam filtering of email messages. So you want to label those which are spam and those which are not spam. Similarly, when I said dog and this is all happening in the case of image recognition. A lot of work which has happened in image recognition. And for us, it is also in classification tasks. Whenever you want to label something, want to find out high performance versus low performance, those which are prone to frauds, those which are not prone to frauds. In all of this, larger the data set that is available, the bigger it is, the better it will learn. And that learning, the better it will show up as a good approximation on unobserved or untrained data. So the more data you feed in and the training set, and that is of course a function of the total number of sample points available to you, therefore it is called that is why big data and machine learning, and as I showed you, the largest number of applications that are coming up in economics is in the space of finance, where you do have access to a lot more data than in the rest of social sciences. Yet, there is another area of social science, and that is when we are using data generated by social media, for instance, and we are using that as data. There also you have a lot of data. So in these spaces where you're using data generated by social media or data in finance, there is a lot of data. It has become a fertile ground, as Holverian is saying, that economists now have a lot of data. The second thing, but I also want to tell you, machine learning models, because there is that, because it is an ill-posed problem, the functional flexibility is so much, it is there. Even if it is a small data, you can fit something like a decision tree. And the decision tree, because it is a flexible functional form, the tree, you can just stop the tree, it will start to see, because the sample point that you have in this Titanic data set is not very large. So the total number of 300, 400 odd data points that you have, and there also you can try out some machine learning techniques. So uh, though in a traditional sense, yes, it is true that machine learning models really need big data. So therefore, big data and ML, and that is when ML has made an advance and is coming into economics, because we are no longer in data poor environments. But some bit of recent work is also happening in applying machine learning to data poor environments. Secondly, because the functional forms that we fit can be very flexible, we can actually work with a few machine learning models in data poor environment. So yes, that is the answer to your question.
Yeah, thank you. It
Anand,
was very nice. One more thing I want to add here.
Akriti,
So
can
when
you
we,
please switch on your camera? It
I
would be
tried
nice.
earlier, but it
Yeah,
was not working.
yeah.
Is it
Now,
working now?
yeah. Now we
Yeah.
can see.
Okay.
Yeah.
So one more question: when we talk about big data generated through social media and finance data from stock market or something like that, most of that data is very unstructured. So
Yes.
do we face any problem? Like if you have used it, for your
Yes.
research. So did you face
Yes.
any problem? Because I find it very tiresome. If I get hold
Yes.
of that unstructured data, like how to go about it, even if I get the data, huge amount of data, but then where to go from there? To get
Yes.
lost somewhere
It's
in
a very
between.
good question. Yes. See, when data, as I said, it would not have gained this kind of popularity if it needed too much structure. It does work with unstructured data. To the extent of this, suppose in standard econometrics, so whenever we teach statistics, right, we know we have a problem of degrees of freedom, right? That is something we always tell our students, right? So we are limited by the total sample size that we have. So if this is a regression exercise which is going on and you have too many explanators or independent variables, we know that we will run into a degree of freedom problem, right? Because our there will be a problem in whenever we want to estimate the partial effects of any of the independent variables in too many independent variables, right? Let's say this exercise itself, I want to predict, or I want to talk about what drives firm's performance, and I think there are a lot of variables which explain firm's performance, right? So that means I am in a situation where there are a number of independent variables, which are typically called features in the context of machine learning. But I have a number of factors which I may think as independent variables. In the standard way of doing econometrics, we typically have a problem of we try to this kind of data where there are a lot of possibilities among the total number of variables which are available to us. This is called fat data. You have a kind of structure where the data is fat. It's too many explanators, for instance. So you want to reduce the dimension of the data. Dimensionality reduction is one of the things that we have to do. And but when it comes to machine learning, one advantage is you can actually work with fat data. Okay, so you can have as many explanators as you want. There are boosting techniques. I have myself experimented with a kind of boosting algorithm called extreme gradient boost. And there, unlike in the standard logistic regression which we ran, where we had problems of degrees of freedom, we could only use a subset of those variables as independent variables. In the machine learning exercise, we actually used it to for the purpose of dimensionality reduction as well as prediction. So we fed in all the possible regresses. We said, okay, use all of them as input. whichever ones, whatever pattern you see, and the machine or our program dropped out a whole bunch of those independent variables and picked out only a subset of them. Very interestingly, without knowing, it cannot tell me why it is doing so, but it did. It picked out only 2 or 3 of those variables and said, these are the ones, and in terms and ranked in order of degree of importance, are the ones which seem to have the greatest influence on firm performance. Okay, so to the extent that you can have fact data can be dealt with. That is, you have a large number of independent variables. You don't know what. So the process of dimensionality reduction is one of the functions that can be done using machine learning tools. Now, of course, in economics, we have been using principal components analysis already. We know that, but PCM itself it has you can do principal components analysis using a machine learning approach. So one confusion that people have is, what really is machine learning then? If you say principal components analysis, I can do, so I can basically approach the problem like this. I don't know, I have a whole bunch of independent variables. I have to reduce the dimension. Round one, I do a principal components analysis. I reduce the dimensionality of the data. And then I run a smaller, where I run my standard logistic regression or whatever, or even I do a non-parametric regression where the functional form can be anything, I fit it. What would be the difference from a machine learning kind of exercise? Well, in machine learning, the first approach, which is different, is that step one will be different. You won't take your entire sample available to you and feed it to your, regression exercise. Okay, so you would be splitting the data into the training set and the test set. So it is what you would, and you would ask for this internal validation that what you learn in the training set, are you learning it? You will test for it in the test set. And then say, okay, this is a good fit. This is the kind of functional form with which I will be working with. Okay, this is a good fit to the data. Okay, so the approach is slightly, so you can do a principal components analysis as per the machine learning approach, and you can also use fancy machine algorithms which will directly do a dimensionality reduction for your data. The big difference when you go the machine learning route is that step one, that separating your data into 2 parts, the training set and the test set. This is something that we typically do not do. And Holverian is claiming that because economists now have a lot of data available to them, the size of data is not small, we have no excuse anymore not to do this kind of internal validation. Why are we taking the entire sample together and then fitting our entire model? So a kind of best practice which is becoming now common in econometric exercises, whether or not you use a machine learning algorithm. Okay, algorithm is a different part, where I told you about the find S algorithm, right? You have other algorithms. You have the support vector machine as an algorithm. You have various decision trees as algorithm. Whether you or not you apply a machine learning algorithm, an approach to the data that we can talk of is this bifurcation of the data, and then you run a standard, regression tree, or you not regression tree. You can run a standard logistic regression that we are used to in economics. Okay, so the big difference here is how you treat the data. In machine learning, you have this because because it is an inverse problem. The treatment of it is you will be using a training data and a test data, and you will try to infer that functional form by seeing how it performs in that unseen data. So that is the difference. So you can, to that extent, to some extent, unstructured data you can work with. If there are correlations within variables, we typically have problems, right? If you have problems of multicollinearity, this can work with that. Even if there are problems of multicollinearity, you feed in all that fat data, There are no problems with these models. It will automatically detect it and take care of it. But if the data is tremendously noisy, you will need a lot of training data for it to understand the noise. There is no free lunch. There's no, there are trade-offs out here. So absolutely unstructured data or very noisy data that we've seen, even prowess that you work with, CMI prowess data, is actually very noisy. We have had to, even before working with a machine learning model, we have had to Winsorize it. The outliers, we had to remove it. So too much noise with data, after all, is finite. With a certain amount of finite data, if there's a tremendous amount of noise in that data, this also will not work. The predictions will not be very good. And if there is the structure, but yes, so if the functional form can be flexible, it can work with fat data. It doesn't have to bother so much about issues of multicollinearity. So there are benefits to it, and the approach of using as part of it as training data, you have an internal validation of it, and the test data, that is definitely a benefit. But too much noise, no, it did not work for us.
Thank you.
Debdatta, in this context, if I have understood correctly in your training program at SAU, I think
Yes.
in regression analysis is based on method of least square. So we try to
Yes.
minimize the square of errors. But here we use this, favorable cases and the odds. That is
Yes.
another advantage, I think, that conditional
Yes.
probability kind of things.
Yes. So
That
here I didn't go into that. Here there is an idea. The whole idea is comes from something called a structural risk minimization. So from estimated, so there was a lot of work which has actually been done by the Russians. Vapnik, and there's a C person, I can't pronounce his name. So they were the Vapnik, a lot of work which was done in statistical learning theory, okay, which is the background basis of this. So when I said that, you have this, how do I, so you have this ill-posed problem. You're going to convert it into a well-posed problem. When you convert it into a well-posed problem, you want to see how well it is learning, right? So when you want to see how well it is learning, instead of the way you have in a least squares approach, you have here also you have a loss function, by the way. But the loss function is treated very in a slightly different way. So that will be slightly technical. So if you want to know further, I can discuss that with you. But yes, it goes
Sure.
beyond the least squares approach of the
Yes.
loss function that you have in the least squares, our standard least squares approach. This is based on an SR, structural risk, or an ERM principle, an expected risk minimization principle, which comes from statistical learning theory, which is slightly different from what we are used to working with. Yes.
I think Hanan, are you there? Hanan wants to ask something.
Hello.
Hanan, yeah, please
Yes,
go
hello.
ahead.
Am I audible?
Yes.
Yeah, thank you, ma'am, for the great talk. So before I ask, I would just like to give a idea of my background. I have done engineering in data science and AI/ML, and then I did my economics PG from JNU. So one issue that I always have while
Hanan, can you
in this
speak little slowly?
oh, I'm so sorry.
That's okay. Yeah.
Yeah, so one issue that I always have in this interdisciplinary approach of like tech and social sciences is when I'm dealing with unbalanced data sets. So often while modeling for unbalanced data sets, it is these black box unsupervised algorithms that perform the best. For example, as you mentioned, XGBoost or random forest, that will perform the best. So, but that is good for when we're dealing with, say, business data or some marketing or finance data. But in the field of social sciences, when it can have policy implications, this underrepresentation of some minority groups in data and this sort of future engineering where we are removing the layers or finding the best parameters might have large implications for those groups that are underrepresented in unbalanced data sets. So what do you think is the normative value of using such black box unsupervised modeling methods in policy and social sciences?
That's a very interesting question. Where partly you already see. I'm not. I wanted to present this as a critical appraisal of machine learning. I'm not arguing. I'm saying there are trade-offs. So uh, as you're saying, so these models, these are being seen as prediction machines. They do predict very well. But the problem is what they predict, they cannot communicate with us because it is not human intelligence. So they see a pattern and they say so. So we also had that. We faced that, the machine just told us these two variables, that's it. So there are number of situations, and there are more other than the issue that you're saying about underrepresented minority populations. There's also a problem in, and let me bring in this thing, the way you set up your training data might also have your researcher's bias. That is, you when whatever you treat as your x variable and y variable and feed it into your computer program, and this is seen in the context of usage of algorithms in the context of employee in hiring processes. So when you try to automate processes of hiring, for instance, in this digital age, large number of companies are doing that. For public policy, it's a very big matter in terms of employment. If you suppose you say you automate everything and you use these ML algorithms, and also it goes to the, you also want it to decide for you. You take it straight up to AI, then at least the ML part, you say that, it'll learn the patterns it learns from. So all CVs will be, you break it up into features of the CVs. So I'm giving you a public policy example, a policy problem, which can be coming from the labor market out here, that I'm going to, use machine learning algorithms to find out who should be the, the best possible fit for a particular job. So what I fed, so I'll get my machine to learn. So I'll feed in some CVs to the machine. So my training data, apart from this, so it will just be that, I myself have some human biases and well-known biases, it may be. So certain groups, certain, educational background, certain things I will prefer. Partly, I think you're also referring to something of that sort. So the minority, the whole problem will become intense now because the machine will only learn from that biased sample. So, and then the prediction that it will do in the unseen test data will reinforce the bias. Well, is there a correction? No, other than saying you use multiple, and there are other advances, but does that mean machine learning is useless? No, it comes from another class of machine learning called adversarial machine learning. So you can now actually change the training data. You have to ensure that the learning is as diverse as possible. If you can do that, then to some extent, this problem of bias, and now there are a lot of algorithms which are called bias corrected, and correction for these built-in biases, which may come from the fact that the way I set in what was my training data, as a large number of underrepresentation problems, biases, how do I correct for it? Well, the only thing is to tell the modeler and to request of these algorithms that the training process of the learning process itself be as diverse but that will need a lot of data. It'll need access to, so but as technologies move and you have access to a lot of data, maybe these many of these hiring websites, the more you have these access to data CVs which are available online, the more you learn from them. And this, which is what is happening with ChatGPT, for instance, when you have you're learning from the way you use common language, you learn a lot more because people are using chat. The more it is used, the more it will learn. Well, then you can potentially put in a bit of correction, but per se, if your training data is biased, then that bias will be further reinforced in the test data, and that is a huge public policy concern. So I am in complete agreement with you that if you, how do you know what, how do you allow for appropriate training with these methodologies? They are not all, and all good, and you have to be very careful about this, right?
I think
And there's a
yeah.
literature for labor markets where you use as an economic student, if someone wants to learn ML techniques for economic
Some reference
research,
book,
can you suggest some start?
some
Uh,
reference book or something basic, very
so,
introductory type.
so the point is for economists reference book. So I have learned from interesting papers, for instance. So right now, I wouldn't say there's yet a book for economists. There are good books for, computer science. There are good books in machine learning per se. But Susan Athe, for instance, has a good set of papers with Mulena, and then Anne Mulyanathan, and then there is Grimmer et al. Grimmer in American Political Science Review, which I can share with you. Give a very nice detailed. So I would say a set of good papers and a few classic books on statistical learning theory, because when you go to machine learning, it's good to actually know, what is the fundamental toolbox which this is using. This is a very different tools. The approach is different. The modeling is different. Statistical learning theory has a whole different, the inductive approach that they have to data. That needs a little bit of understanding. So I can share that with you, and you can send across to her, whoever want to know about, this. But largely, machine learning for economics, in the context of classification problems, in the context of prediction problems, and in the context of dimensionality reduction, fact data reduction, choice of appropriate predictors. This has been, this is well understood by now. But in the context of causality, and there, as I think I mentioned this in the workshop, machine learning is not yet, it has, so I didn't bring the technical, the bias trade-off. Machine learning does well because it fixes incredibly flexible functional forms. But when you fit these functional forms, you have to, your estimates will be biased. You will be having biases in the estimates. You have to tolerate that bias. Now, because of that, the bias will come in when the way we understand, you really cannot directly use machine learning models. You have to correct for that. And that is very cutting edge work, which is happening now, which is called double machine learning or double debiased machine learning, which means, so all of this, that's why there is no, I don't see any good economics textbook which will walk you from classification to prediction to causality to dimensionality reduction, all the things that we need to do. But there are lots of good research papers which look at separate dimensions of this classification, prediction, dimensionality reduction, and these newer approaches which need to be modified when it comes to causality, right? So I can give you separate references for these things,
Maybe
separately for
now
classification.
you have to write one. You have to write a book on ML for the economists.
Yeah, I'll have to de-jargonize, and you have to, the problem will be creating a common language. We
Yes.
call independent variables, they call them features.
Yes, like
Feature
that. Yeah.
selection. So for us, you see, the whole thing is we know what our independent variables are because it's a, so when we talk of causality, we have a y variable and our x variables, which are our independent variables.
They call
Our
it
theory,
attributes.
we have a good bit of theory because it's a deductive approach, right? We know,
Yes.
so these are likely to be our, but
Correct.
there it is called feature selection. The whole
Right.
the objective is to find out which of these ones will be your good. So the feature selection, but the features are the very fact the features are your independent variables or your attributes will require a kind of standardization of terminology. So whenever two disciplines speak, I think the biggest challenge is this common space or vocabulary
Language,
which
yes.
has to emerge,
Hmm.
and the move from deductive to inductive, and why to make us become inductive, and the gains to us and the loss to us, all of that has to be put together. So I guess the neat takeaway should be that for us to use these black box models, we need a lot to convince us yet. As far as prediction is concerned, yes, you can, that's why the adoption of these techniques and by corporate sector firms who will say at the end of the day, give me a black box which predicts very well. I'm happy with it. I don't want to question how it did it. I want to see it doing very well. Well, it is well understood. And the academic sense, you need to do a lot more work. Maybe inductive machine learning, the work which is happening, the predictive power, where not only is there is predictive power, but you have explanatory power with it. That is very recent work which is happening in machine learning itself.
Absolutely.
Yeah.
Sadiq, do you want to ask any question to your supervisor in public? Sadiq, are you there?
I think he either has run away or I don't think he wants to ask me a question right now.
Okay.
Or
No,
Sadiq, are you there?
He
yes,
is
ma'am.
there. Do you
Yes.
want to ask anything?
Uh, Not now, sir. It's been
Okay.
a long talk, and
Yes.
I guess there were so many questions. So
Yes.
I will,
Sanjot is saying thank you. Thank you
yes, sir.
very much.
Thank you,
And
sir.
yes, others are also saying thanks, Harshit and Praneta and so on and so forth. So, of course, it was a fascinating lecture. Thank you so much for all your efforts. I think it would be very effective also. Those who are interested, they can get in touch with you in future. Of course, Debdatta is a friend. We were together in JNU during our student days and so on. However, formally on behalf of Delhi Economic Society, we must express our gratitude for all your efforts. And it was very useful lecture. With your permission, we would just upload it in YouTube. So later on also people, those who are interested, they can get benefited out of it. And
Right. Yeah.
maybe we'll share your some contact ID, or in your website probably your contact ID would be
Yes,
available in
it's
some
there. Yeah.
website. Yes.
Yeah. Yeah.
So if someone wants, they can get in touch with you easily. So
Yes,
thanks a
absolutely.
lot, Debdatta.
Yeah.
We
Yeah.
are extremely grateful.
Thank
Thank
you.
you so
Thank
much.
you.
Thanks a lot.
Yeah.
Thank
I'm thankful that you, spared a Saturday evening, all of you. It was very hard to decide how, because it is actually very technical, but how to make it, to make
But you
sense
have
out of
done a
very
great
technical
job.
things.
Yeah, you have done a great job.
Uh,
Hopefully, I mean,
so
you are new to
I
this.
hope,
And
yeah, for those new to this there are many ways of seeing the problem. So I brought out a few aspects of it. I didn't even bring up text, but there are many things which can be done with text also, and with unsupervised learning also. Yeah. Yeah.
these are newly emerging areas of economics. So,
Yes.
in our Delhi Economic Society, there are a lot of teachers who are teaching at undergrad level in Delhi University and elsewhere. So,
Yes.
in future, in the years to come, probably they would try to introduce some of these new things in
Yes.
undergrad syllabus of economics. So,
Right.
going forward, so that would have enormous multiplier effect, of course.
Right.
Let's
Right.
see how it works. But it
Let's
was a
see.
great introduction,
Yeah.
and we would hope to get you again for other lectures in future.
Sure.
So,
Sure. Sure. Anytime. Okay.
thanks.
Thank you, Shubhaj.
Thank
Thank
you.
you.
Thanks,
Thank
Devdutt.
you.
Bye. Bye.
Bye.
Thanks a lot, other participants for active participation and for your for paying attention. So thank you very much. Thanks a lot.
Right.
Okay. Bye. Thanks.